Assalamu alaikum and very good evening to all of you. I hope you had a good day so far. My dear followers, students, colleagues, ladies and gentlemen, in this video I am going to prove how elasticity of substitution is constant, and if it is constant, what does it mean? Whether there will be a single value of constant elasticity of substitution production function, or it varies in a different situation. So in this video I'm going to prove that. I'll discuss first about the constant elasticity of substitution production function, a little bit of its history and various functional forms. Then I would like to derive model of technical substitution for the two inputs or between two inputs, and then I would like to try to derive how we can calculate the value of the elasticity of substitution, that is sigma, using a constant elasticity of substitution production function. So as it is clear from the name of this production function, the elasticity of substitution associated with the CES will be constant. This production function was originally introduced by Arrow and others in 1961, and the following form was used for this production function, where Q is a function of Q is the output, which is a function of labor and capital, and that is equal to K raised to the power rho plus L raised to the power rho whole raised to power gamma divided by rho. In this production function, rho is not equal to 0 and it is equal to or less than 1. Gamma is greater than 0. If gamma is equal to 1, then there will be constant return to scale. If this is greater than 1, there will be increasing return to scale, and if this is less than 1, then there will be decreasing return to scale, but it is necessary that gamma should be positive, that is, it should be greater than 0. Here I have forgotten the equal sign, so there is a equal sign in this slide. In this production function, this is the distributive parameter. This this is substitutive parameter. This represents substitution, and gamma refers to returns to scale. This function closely resembles the constant elasticity of substitution utility function that I have discussed in greater detail in the previous videos on consumer economics or consumer theory. Although we have now added the exponent gamma upon rho, which permits explicitly introduction of returns to scale, as I mentioned earlier. For gamma greater than 1, the function accords to increasing return to scale, and if gamma is less than 1, then it accords to decreasing returns to scale, and in case gamma is equal to 1, then there will be a constant returns to scale. More often, the CS function is used with a distributional weight alpha, where 0 is less than or equal to alpha is less than or equal to 1. So alpha take value between 0 and 1 to indicate the relative significance of the inputs. So we may write the above function, which was originally used by Arrow and others, in the following fashion, where Q is equal to function of capital and labor, and that is equal to alpha times K raised to the power rho plus 1 minus alpha L raised to the power rho whole raised to power gamma divided by rho. Now here in this CS production function, we have one additional parameter, that is alpha and 1 minus alpha, and this is basically distributive parameter. So this is distributive parameter, and rho is a substitutive parameter, and Gamma basically stands for return to scale, that indicates return to scale. So as I mentioned, alpha and 1 minus alpha are distributional parameters. Rho is a substitution parameter, and gamma refers to returns to scale. If there was a capital A here, then that would be just like efficiency parameter or the state of technology, which is also present in Cook-Douglas production function. It will be easy to verify that the constant elasticity of substitution function exhibits constant return to scale. So usually gamma will be equal to 1. So in most of the CES production function, you will see 1 upon rho. So when there is 1 upon rho, then it means that there is constant returns to scale. But this is the generalized function of the form of the CES production function. It will not be surprising for us to discover that the constant elasticity of substitution production function has a constant elasticity of substitution that can be easily verified. So given that the CES production function is of this form, as I mentioned earlier in the previous slide, so we may calculate the partial derivative of q with respect to L and partial derivative of q with respect to k. So when we take partial derivative of q with respect to L, that will give us marginal physical productivity of labor. And if you do that, we will use the power function rule and then the chain rule. So if I take partial derivative of this function with respect to L, then I will bring this down. So I have gamma over P here, and then I will write the whole function like this, raised to the power gamma upon rho minus 1. This is simple power function rule. And then the chain rule, now I will take derivative of this with respect to L. So its derivative with respect to L is equal to the power of L, that is rho, that will come here, and then its coefficient 1 minus alpha, and L raised the power rho minus 1. So I can cancel out this row with this row that is written in red. So then we are left with this production function gamma times bracket alpha k raised the power rho plus 1 minus alpha L raised the power p whole raised to the power gamma minus rho upon rho. So if I subtract 1 from gamma upon rho, then I get this. So I can further simplify this, and then I can write this in this function, and that is basically equal to marginal physical productivity of labor. Similarly, I can also take partial derivative of this function with respect to capital, that is k, and in the same fashion, finally, the marginal physical productivity of capital will be equal to gamma times alpha k raised to the power rho minus 1 bracket alpha k raised to the power rho plus 1 minus alpha L raised to the power rho whole raised to the power gamma minus rho upon rho. So that is marginal physical productivity of labor. We also know from the basic microeconomic theory that if we take the ratio of the marginal productivity of the two inputs, that is marginal physical productivity of labor and marginal physical productivity of capital, that is equal to marginal rate of technical substitution between labor and capital, and in turn this is equal to partial derivative of q with respect to L divided by partial derivative of q with respect to capital, and that will be equal to, I will use this as a numerator because this is the marginal physical product of labor, and here I will use the denominator, and that will be the partial derivative of the production function with respect to capital. So some of the things are common, so these will be cancel out. For example, gamma in the numerator will be cancelled out with the gamma in the denominator. Similarly, this term, that is the production function, CES production function, is in the numerator and the denominator. So both of these will cancel out. So we will be left with the 1 minus alpha divided by alpha into the ratio of capital to labor whole raised to the power 1 minus rho. So Malner rate of technical substitution between labor and capital is equal to the ratio of 1 minus alpha upon alpha, which is constant, times k over L raised to the power 1 minus rho. So let us suppose, in order to simplify this, let me define that R is equal to the ratio of capital and labor. Then I can write the marginal rate of technical substitution of labor for capital as 1 minus alpha divided by alpha times R raised to the power 1 minus rho. So R is basically replacement for this. If you take natural log on both sides of this equation and dividing through by d natural log of R, then we get this natural log of MRTS, natural log of 1 minus alpha divided by alpha plus natural log of R raised to the power 1 minus R. So if I take the derivative of this with respect to natural log of R and also here, then this will be 0. So we will be left with the derivative of the logarithmic derivative of Malner rate of technical substitution with respect to natural log of R, and that is equal to this, which is equal to 1 minus rho. So we have this, and since we know that sigma, which is equal to the logarithmic derivative of R divided by the logarithmic derivative of the Malner rate of technical substitution. So the reciprocal of this will be equal to 1 divided by 1 minus rho. So this is the logarithmic derivative of R, which is the capital labor ratio, and this is the logarithmic derivative of Malner rate of technical substitution. This numerator would mean derivative of R divided by R, and this will be equal to derivative of MRTS divided by MRTS, and if we simplify that, then we finally get 1 divided by 1 minus rho. So this is the elasticity of substitution in case of constant elasticity of substitution in production function. Now this is constant. One is constant, and rho is constant. So it means that the magnitude of sigma, or the value of sigma, is constant, which is equal to the ratio of 1 to 1 minus rho. So the magnitude of elasticity of substitution in CES function depends upon the value of rho. So I'll show that. So this is what I said earlier, that this logarithmic derivative of R is equal to this, and this logarithmic derivative of MRTS is equal to this, and finally we can write it like this, and it is equal to 1 divided by 1 minus rho. So as I mentioned earlier, sigma is constant and its magnitude depends upon the value of rho in the following fashion. If the value of rho ranges from -1 less than rho is less than 0, then in that case elasticity of substitution will be greater than 1. If rho is 0, then it implies that the elasticity of substitution is equal to 1. If 0 is less than rho is less than infinity, then in that case the elasticity of substitution for the CES production function is less than 1. So the difference is, keep this in mind, that although the elasticity of substitution for constant elasticity of substitution production function is equal to this, however, its value depends upon the value of rho. If rho assumes value in this range, then sigma is greater than 1. If rho assumes the value of 0, then in that case elasticity of substitution is equal to 1, and then the CS production function converts to Cobb-Douglas production function. If rho takes value between 0 and sigma, in that case the value or the magnitude of elasticity of substitution is less than 1. So this is very straightforward and very interesting. I know majority of the students and colleagues are confused and they don't know, but if you watch this video thoroughly a number of times, then it will be easily understandable for you. Kindly subscribe to this channel and don't forget to click on the bell icon so that you could get regular notifications about my videos that I'll upload for my students, for my colleagues, and for my followers. Thanks for watching this video. Kindly share various videos of this channel in various WhatsApp groups and on social media so that this could reach to the maximum possible number of people. My dear followers, I feel pleasure when I share my knowledge, my experience, and these videos with my colleagues, with my followers. And I am doing this for the benefit of the community of the students and my colleagues and followers of this channel. Thank you, and